Welcome to SS2 Chemistry, Term 2, Week 4. Intermolecular forces are the attractive forces between molecules, not within them. Intermolecular means within. Although weaker than covalent or ionic bonds, intermolecular forces determine the physical properties of substances: boiling point, melting point, solubility, viscosity, and surface tension. By the end of this lesson, you will define and compare van der Waals forces, London dispersion and dipole-dipole, explain hydrogen bonding and its unique properties, apply these concepts to explain anomalous properties of water, and answer WAEC questions on intermolecular forces. Let us begin. Van der Waals forces are weak intermolecular forces named after Dutch physicist Johannes Diederik van der Waals, 1837–1923. They have two types. Type 1, London dispersion forces, LDF, also called temporary dipole-induced dipole forces or van der Waals forces in the narrow sense. All molecules experience London dispersion forces. In a nonpolar molecule, e.g. H2, Cl2, CH4, noble gases, electrons are distributed symmetrically on average. However, at any instant, electron distribution can be uneven, creating a temporary, instantaneous dipole, a slight positive end and a slight negative end. This temporary dipole induces a dipole in a neighboring molecule. The result is a weak, temporary attractive force between the two molecules. Strength of LDF depends on number of electrons in the molecule. More electrons equals larger, more polarizable electron cloud equals stronger LDF. Surface area of contact. Longer molecules have more surface area for LDF interactions. Examples: noble gases, He, Ne, Ea, Ka, Se, are held together only by LDF. As molar mass increases from He to Se, boiling point increases, He minus 269 degrees Celsius, Se minus 108 degrees Celsius. Alkanes, CnH2n plus 2 methane with CH4, boils at minus 162 degrees Celsius, propane, C3H8, at minus 42 degrees Celsius, octane, C8H18, at 126 degrees Celsius. LDF increases with chain length and number of electrons. Type 2, permanent dipole-dipole forces. Occur in polar molecules, molecules with a permanent dipole moment due to electronegativity differences. The positive end of one molecule attracts the negative end of another. Example: HCl, HBr, HI, all polar due to the electronegativity difference between H and the halogen. Dipole-dipole forces are stronger than LDF for molecules of similar size because they are permanent. Hydrogen bonding is a special, strong type of dipole-dipole interaction. A hydrogen bond forms when a hydrogen atom is covalently bonded to a highly electronegative atom, F, O, or N, collectively called FON, with a lone pair, and is attracted to a lone pair on an electronegative atom of a neighboring molecule. In notation, written as XH, Y, where X and Y are F, O, or N, the dashes represent the covalent bond to H and the dots represent the hydrogen bond. Hydrogen bonds are approximately 5 to 10 times stronger than ordinary dipole-dipole interactions, but approximately 10 to 20 times weaker than covalent bonds. Examples of substances with hydrogen bonding: water, H2OO is highly electronegative. Each H2O molecule can form up to 4 hydrogen bonds, 2 as donor via H atoms, 2 as acceptor via the 2 lone pairs on O. Water is a 3D hydrogen bonded network. Ammonia, NH3N, forms hydrogen bonds, 1 as donor, via H, 3 as acceptor. Hydrogen fluoride, HF, strongest H bonds due to fluorine's extreme electronegativity. Ethanol, C2H5OH, and all alcohols, OH group forms H bonds, explains miscibility with water. DNA double helix, hydrogen bonds between complementary base pairs, LAT, 2 H bonds, GC, 3 H bonds, hold the 2 strands together, can be separated, denatured, by heating and reforms on cooling, renaturation, critical for DNA replication and PCR. Water is one of the most unusual substances on Earth. Its anomalous, unexpected, properties arise from its strong hydrogen bonding network. Anomaly 1. Unusually high boiling point. The boiling points of hydrogen compounds of group 16 elements are H2S, minus 60 degrees Celsius, H2C, minus 41 degrees Celsius, H2T, minus 2 degrees Celsius, all lower than expected for their masses. But water boils at 100 degrees Celsius, far higher than the trend predicts. This is because water has strong hydrogen bonds that require extra energy to break. Without hydrogen bonding, water would be a gas at room temperature, predicted BP approximately minus 80 degrees Celsius, life as we know it would not exist. Anomaly 2, maximum density at 4 degrees Celsius, ice floats on water. Most substances are denser as solids than liquids. Water is most dense at 4 degrees Celsius. Below 4 degrees Celsius, water expands as it cools. The hydrogen bonds force water molecules into a more open hexagonal lattice in ice. Ice is approximately 9% less dense than liquid water and floats. This has profound biological implications. Lakes and ponds freeze from the top downward. The ice layer insulates the water beneath, allowing aquatic organisms to survive winter. If ice sank, lakes would freeze solid and aquatic life would perish. Anomaly 3, high specific heat capacity. Water requires a lot of energy to raise its temperature. The hydrogen bond network acts as a heat reservoir. This explains why coastal climates are milder than continental climates, why water is used as a coolant in car engines, why the human body, approximately 60% water, maintains a stable temperature. Anomaly 4, high surface tension. Water molecules at the surface pull inward, maximizing H-bonds. This creates a strong surface film allowing water striders to walk on water and droplets to form spheres. The like dissolves like roux, polar solvents, water, dissolve polar and ionic solutes, nonpolar solvents, kerosene, benzene, hexane, dissolve nonpolar solutes. Solubility of alcohols, methanol, ethanol, and propan, 1-OL are fully miscible with water. Their OH groups form hydrogen bonds with water. As chain length increases, the nonpolar alkyl chain disrupts the water H-bond network. Butanol is partially miscible, hexanol is practically insoluble. Solubility in biology, glucose, 6 OH groups, is very soluble in water. Fats, nonpolar, are insoluble in water but soluble in organic solvents. Boiling point comparison, H2, minus 253 degrees Celsius, LDF only, HCl, minus 85 degrees Celsius, dipole and LDF, HF, 20 degrees Celsius, strongest H-bonds in the group 17 hydrides, H2O, 100 degrees Celsius, 2 H-donor positions and 2 lone pairs. Viscosity. Water is less viscous than ethanol. Ethanol has longer chains, increasing LDF and stronger H-bonds per molecule. Glycerol, 3 OH groups, is much more viscous than water. The viscosity of oil, crude oil. Nigeria is a major producer, is important in pipeline design and drilling operations. Key points: intermolecular forces hold molecules together, weaker than covalent/ionic bonds but determine physical properties. London dispersion forces, LDF, temporary dipole-induced dipole, affect all molecules, increase with molar mass and electron count. Dipole-dipole forces, in polar molecules with permanent dipoles, stronger than LDF. Hydrogen bonding, special strong dipole-dipole, H bonded to F, O, or N attracts lone pair on F, O, or N of neighboring molecule. Anomalous properties of water due to H bonding, high BP, 100 degrees Celsius, max density at 4 degrees Celsius, ice floats, high specific heat capacity, high surface tension. Like dissolves like. WAEC chemistry questions on intermolecular forces require naming the correct type of force, explaining anomalous water properties, comparing boiling points of related compounds, explaining solubility trends. All explanations must reference the specific intermolecular force by name.